Okay, all right. Okay, all right. Anyway, so welcome back. And so today we'll talk about the different threats to quantum computing systems by overviewing the different threats and starting to talk about the different threat models. So there's a very brief introduction to some quantum computing topics just to set a context for the different threats that we'll talk about. So when we have the lectures about quantum computing, we'll kind of talk about this again. But you might have seen sort of some equations like this that define a qubit. So in quantum computing, we deal with qubits, which are quantum bits. You can also think of them as quantum registers. I think the best analogy is a qubit is sort of it's a register that holds a piece of data, and then you're applying different operations to manipulate that. So a quantum bit or quantum register. And in quantum computing systems, the qubits are made out of superconducting qubits, trap bands, or different kind of physical realizations. But each qubit can basically have two basis states. So cat0 and cat1 are the basis states of the qubit. And then, so the qubit is defined basically by this equation that tells you what are the probability amplitudes associated with each of these basis states. And the basis states can be something like, spin up or spin down, or different energy levels in superconducting qubits. So this is sort of independent of how you actually realize the qubits. And then when we talk about the amplitudes, one of the key important things is that the amplitudes tell you the probability of measuring that state when you actually measure the qubit. So qubits basically they can be in any superposition of the states, but when you actually measure and read out the qubits, you end up with a binary 1 and a 0. So these amplitudes tell you what is the probability, alpha squared is the probability of you find a qubit in the 0 state, and beta squared gives you the probability that you'll find a qubit in the 1 state. So this becomes important when you measure and actually read out the qubits. And there's some constraints that the A and alpha and beta are complex probability amplitudes, and they have to satisfy this equation where they add up to 1. And then this is just for one qubit. Of course, one qubit, you can't really do much. So typically you have, your circuits or your system are made out of multiple qubits. So for example, for a 2-qubit system, the equation gets expanded. So with 2 qubits, now you have the 4 possibilities for the basis state. So with a 2-qubit system, it could be in 0, 0, 0, 1, 0, 1, 1, 0, or 1, 1. These are the 4 possibilities. And again, each of those possibilities is associated with some amplitude. So we'll talk about later measurements. So when you finish a computation on a quantum circuit, you measure, and then you get these probability outputs of, what's the probability of circuit being in state 0, 0 versus 0, 1 versus 1, 0 or 1, 1. And then when you have a system that's made of multiple qubits, there may or may not be entangled. So we'll talk about entanglement later. But if they're entangled, that means that basically certain outcomes might not be possible, or there's some correlation between the outcomes. But still, you have different amplitudes associated with the different combinations. So we'll see when we talk about the different security attacks. We'll see how, for example, an attack might change the output probability. So for example, a security attack might change instead of 0, 0 being the most dominant output with the highest amplitude, maybe the amplitude of 0, 0 becomes less, and that modifies the output of the circuit. And then there's the same requirement as for one qubit, that the sum of the amplitude squared is equal to 1, and then each gives you the probability of finding the circuit in that state. We'll again, we define the qubits as this kind of combination of two basis states, and then we call them qubits. But you might hear or have heard somewhere perhaps there are qubits, qudits, there are qmodes. So they're basically different realization of qubits. Or for example, in a qubit, the qubit is actually made up of 3 different basis states. So you can think of it that if you go from qubits to qubits, then you have instead of 2, they have 3 combinations, so you can store more data in the qubit. And then sort of at the extreme case, you have Q modes, which is for continuous variable systems where there's so many different possibilities. So in most of the discussion, we'll focus on qubits, where the system is made of just two levels, 0 or 1. But it's good to know about these qubits and then others that people are exploring. So there could be different realizations of qubits, and then and sometimes actually there's some of the security attacks that we talk about, like higher energy attacks, deal with the fact that you make an assumption that a qubit is a two-state system, but somehow you put it into a third level that's not part of the way the system should operate, and that's how you can introduce some problems. So so this is sort of how you define the qubits, and these qubits can be made of different technologies. So there's superconducting, trapped ions, there's quantum dots, topological qubits. So there are many different ways of realizing a qubit, and the main thing is that for each of the physical realizations of qubits, you have to somehow there has to be sort of these basis states. So for example, for nuclear and spin qubits, spin up would correspond to basis state 0, and then spin down would correspond to basis state 1. And then you can have other ones for photons, either there's a photon or there's no photon. These are different realizations of the qubits and how they map to the basis states. And then among these different types of qubits, also we kind of divide them up into sort of manufactured qubits and sort of let's say I would say qubits that are sort of naturally occurring. So superconducting qubits like IBM, it's a manufactured qubit. It's actually a circuit. There's a Josephson junction and a circuit that's used to create the qubit. Whereas if you have like trapped ions, then the ions, the actual molecules are the qubits, so they're not actually manufactured. So they're very kind of interesting things that if you manufacture like superconducting qubits, each qubit is different because you manufacture it, and there are manufacturing problems. But if you have trapped ions, then in principle each ion is identical by nature, so there's no differences between one ion or another. So there's some interesting features that kind of differentiate them. And most of the class will focus, and most of the security research has focused on superconducting qubits, just because maybe they're more easily available. IBM and other companies made their machines available, but other types are sort of, I think, are equally important and actually underexplored from the security perspective. So just because we'll talk a lot about superconducting qubits doesn't mean that they're much more important. And then so we have the qubit. So for example, you realize a qubit as a superconducting junction. So here you have one qubit, but then to compute you need multiple qubits. So for superconducting machines where you're manufacturing the qubits, they have a fixed layout or fixed topology. So this is an example from IBM, where you see 127 qubits that are arranged in this it's called a heavy hex topology. But so each of the dots is a qubit, and then the qubits are connected together through couplers. So in the future, when we talk about quantum gates and quantum operations, you need, if you want to have like an operation between two qubits, they have to be connected by a coupler. In a superconducting machine, if you want to make an operation between, I don't know, qubit 1 and 126, because they're not directly connected, you have to do some swap operations to get the qubits closer. So there's some constraints for superconducting qubits. For neutral atom machines, where you can actually move the qubits around, then any qubit can sort of connect to any other qubit. So there are many different realizations, but the key part, regardless of the architecture, is that you have something that realizes the qubits, and then somehow you have to connect two qubits together so they can interact for different gate operations. And then so these qubits will be used to realize some quantum system, and then again you have some amplitudes associated with the different states of the system. So we have the qubits, and then to actually operate on the qubits, we have to we apply some quantum gates. So typically, you have a set of quantum gates that you can apply to the qubits to perform the computation, and then the different Hadamard, Pauli, CNOT gates. So the different gates are basically manipulating the state the qubits. And I think the interesting part, um, maybe not relevant for today, but is that all the operations are unitary, which means that you can actually run them in reverse. So every quantum operation, every quantum gate, you can compute it and then you can run it in reverse. So they're fully reversible. Some operations like measurement are not reversible because they collapse the state of the qubits. But for the basis gates, you can run them forward or backwards as well. But where we want to get, so we want to get to this picture that basically to perform a quantum computation, you start with a qubit in some state or a set of qubits in some state, and then you apply these quantum gates to change the state of the qubit, and then you end up in a new state. So quantum circuits basically proceed by repeating this, or you start it with some qubits, you apply some gates to them to transform them, and then you have a new state, and then you continue. And we'll see this type of a picture quite a lot, where basically we're showing the different qubits as the lines, and then sort of the time always goes from left to right, where you apply the quantum gates to the qubit, and then that transforms the state, and then at the very end you do a measurement to actually read out the circuit. So just to map it up, the qubit is in some initial state. Then you apply this quantum gate, which is usually depicted as a box. So you're transforming the qubit. You could have a single qubit gate, or you can have you can see two qubit gates. That means that somehow two qubits are interacting, or even many qubit gates. And then again, after you perform a gate, you end up in a new state. So that's how the computation proceeds. And hopefully you'll see soon why we're talking about the structure of the circuit. But sort of if you so basically the program continues by applying these gates or these unitary operations to the circuit as you're proceeding, and then at the very end you do a measurement. So from the beginning to before the measurement, everything is all the qubits are in their possibly entangled state. And then only when you do a measurement, you actually read out and get the ones or zeros that are the output, and then the ones and zeros that are the output are governed by the output probabilities associated with these qubits. And then lastly, you'll see this picture. We'll have a measurement. So at the end of the circuit, if you actually want to get some information out of a quantum circuit, you perform a measurement to get the data. And unlike the quantum gates, that the measurement is this destructive process. So once you measure, you kind of lose all the quantum information. You end up with a 0 or a 1, which is the binary output of the circuit. So we say that the quantum system is, when it's measured, the wave function collapses, and then basically you end up with just a 1 and 0 according to the probabilities. Okay, so now kind of putting together, and then this will give us a good idea of the different points where there could be a security problem. So pretty much every NISQ quantum circuit follows the exact same structure, that you initialize the qubits into the 0 state, and then some of the qubits are used as an input, and some of the qubits are just used as temporary registers. You might need some ancillary registers during your computation. And then first, you do some state preparation. So like in your computer, if you have some data, you just load it from memory. But currently in quantum computers, since there is no equivalent of quantum random access memory or quantum memories, basically you have to use everything. You start in state 0, and then you transform your state to get into the initial state. So you can think of it like basically all the data in the quantum circuit is hard-coded into the circuit. You basically, the state preparation defines how you go from 0 to what is actually the input data that you want. So in the future, people are working on quantum random access memories. That will be different, but until then, maybe even problematically, all the input data is hard-coded into the circuit, and you sort of first you have to compute to get your data into the initial state that you want, starting from zero, and then you actually do computation on it. So you say that, you do the state preparation to get the data into whatever the input is, and then you actually do the computation, and then finally you measure, and then, for some qubits that are important, you measure. That's where you kind of the output of the circuit comes out from. Some temporary registers are never measured, so the output is not dependent on those. Are there any questions about this structure so far? And then we'll see later in the course also some examples of actually how this looks in code, but in pictures, this is a sort of a typical picture of a quantum circuit, and yes, the extra garbage. Now, if we just expand it a little bit to show more features, so one thing is that, we say the circuit starts in some zero state, but to get the qubits into zero state, you have to somehow reset them. So there's usually some sort of a reset mechanism that is applied to the qubits. Either if it's like a neutral atom architecture, maybe new qubits are provided. If it's like a superconducting architecture, you have to reset the existing qubits. So there's some way of getting fresh or new qubits into the zero state before you do some computation. And then within the state preparation and within the computation, you have a bunch of either single qubit gates or 2 qubit gates. So in principle, you can have any input quantum gate as you wish, but in practice, realizing more than two input qubit gates becomes very difficult. So most of the time, even if your algorithm or sort of the design of the circuit requires a multi-input qubit gate, they're actually reduced or compiled into a set of 2 qubit gates because those can be efficiently implemented. So maybe you can think of it that, like on a very small computer, maybe your algorithm has a multiplication, but the CPU doesn't have a multiplier. So the compiler changes multiplication into a bunch of additions. So this is kind of similar. You might have an algorithm with big gates, but they have to all be reduced to either single or 2 qubit gates. And then an interesting feature, especially for some NISQ circuits, is that you can actually measure the qubits during the execution of the algorithm. So it's called a mid-circuit measurement, and it's same as the final measurement. Basically, you measure the qubit, which means you lose the quantum state, but you get some information, 1 or 0, about the qubit, and then that information can be stored into classical registers. So you also might see you'll see the pictures that the single lines are the qubits, and the double line thing basically is a classical register. And usually, not necessarily, but usually there's a classical register that corresponds to each qubit where you store the measurement of that qubit. But what happens with the mid-circuit measurement and also the final measurement, you store the measurement, the classical 1 or 0. But if it's a mid-circuit measurement, the usual application is that you can then have a conditional gate that based on the measurement, if the measurement was 0, you apply some gate. If the measurement was 1, maybe you don't apply it. So you can have like a conditional application of some other gate. So it's a useful feature that's leveraged in certain algorithms. So a lot of the machines support this called mid-circuit measurement. And then finally at the end, all the data is measured and put into the classical registers, which is where you actually get the result of the computation. And then again, you reset the qubit somehow, and you continue the execution. So again, in the next discussions, we'll talk more about the execution. Like for NISQ machines, since they're noisy, you run this for one circuit many times. So typically like 1,000 shots. So we call them shots. So you execute the same circuit many times. You collect the outputs, and then you get the output probabilities to see what output is most common. So this actually gets repeated many times to get the computation. Right. Are there any questions about this part? Okay, so this is the structure, and then so within NISQ noisy quantum computers, there are different sources of noise and errors, which actually can be abused to create some security problems. So, but first, what are the sources? So one is imperfect gate operations. So all these the reset gate or the single or the 2-qubit gates, they don't have 100% fidelity. There's a very small chance that they do not work correctly, or they can be abused to not work correctly. So various variations like control pulses, like timing, amplitude, phase, can lead to basically the gates not executing correctly or not working correctly. So like in your computer, the CPU is basically 100% correct. But when you do an addition, it does an addition. But in noisy quantum computers, there's some the operations are susceptible to different noises, and if you can perturb them, then they'll give you a wrong result. Then there's also an issue of crosstalk, which basically means that if you do computation on certain qubits, that can actually affect adjacent or nearby qubits, which especially challenging for superconducting machines where again this where the topology comes into play, that if you do some computation on qubit 44 and 45, then maybe 46 and 47 get affected because they're nearby. So again, on your computer, if one processor core does some operation, it has no effect on the other processor core. But in quantum computers, the qubits have this crosstalk problem, which again, if you do computation on one qubit, it could affect something on another qubit. And of course, a lot of the work on designing quantum computers is to actually mitigate these problems. So, a lot of people are looking at, how do you make gates better, or how do you reduce crosstalk? So these sort of, these are getting better and better every year, but they still persist. There are also other things such as called a leakage error. So basically, this means that the qubit might be defined as a qubit with two basis states, 0 and 1. But for example, in a superconducting systems, there's actually many more possible energy levels. So somehow it might escape outside of this sort of two basis states, and then things will not work as expected. And then a last major thing is readout errors. So when you are reading out, actually when you're doing the measurement and reading out the qubits, that might actually itself not be correct. So maybe the computation okay, but the readout is mixed up. So this again, imperfect measurement process can incorrectly detect the states of the qubit. So these are kind of the problems with the qubits, and everybody is working to make these less of a problem, but still they're not perfect. And then so how this connects to security. So then a security attacker can basically try to abuse those to create some problems. So for example, for imperfect gate operations, if you inject some noise, you might be able to change the operations quite easily, which would be a fault injection. Or if let's say for example, like the reset gate doesn't work correctly, then that would be a side channel where some information can be leaked. For crosstalk, actually most of the initial research on security of quantum computers really focused on crosstalk and fault injection, is because gate operation on 2 qubits can affect something that's next to it. Then you can basically maliciously try to do a lot of computation on one set of qubits to try to flip the state of the adjacent qubits. So abusing the crosstalk for fault injection is kind of one of the classical examples of quantum computer security problems. But this also works the other way as a side channel. So if an operation on 2 qubits disturbs something that's adjacent to it, then whatever's adjacent to it can try to detect what's happening on the qubits by observing the crosstalk. So that could be a side channel. So in the side channels, you cannot leak the quantum states. We'll talk about the no-cloning theorem. You cannot actually clone the quantum states, but you can leak, for example, the type of operation or when somebody is doing some computation. And then for like the leakage errors, if you're able to force the qubit into a higher energy state, for example, outside of the basis states, that's like a fault injection where the circuit might stop computing. And then for readout errors, again, if you can cause the readout to read out incorrectly, then you get a problem. But an interesting thing we'll talk about one of the research papers later where actually the readout errors are correlated. So a value on a certain qubit might affect how a readout is done on another qubit. So that could be like a side channel that, by observing how what are the changes in the readout to your qubit, you could try to guess what the values on an adjacent qubit, which would be like a side channel. So basically, while we talked about all the circuit structure and the noise, is that all the sources of noise or errors or imperfections are actually something that people can abuse. And then, okay, so finally, I want to get back to this picture. This whole discussion is basically this is our picture of basically any quantum circuit as this structure, and then you can now with this picture you can have you can have attacks on the reset mechanisms. That if you can't reset correctly, that might be like a fault injection into the circuit. If you're doing some crosstalk, you might incorrectly prepare the initial state, or your computation might be incorrect, or somebody can sense what computation, what gates you're executing. So you could attack the gates. There's some issues with them. So if that measurement is done incorrectly, then the conditional gates are not going to execute correctly. And then again, on the measurements, you could get wrong measurement or kind of figure out what an adjacent qubit measured. And then also, if at the end, if the reset is not done correctly, then that would be like a side channel. So when we think about the threat models, especially focusing on quantum circuits, basically you have to think about all these different problems. So it's kind of like the attack surface that we talked about. That this is sort of the attack surface, and then somebody might just need to find one of these problems to actually make the circuit compute incorrectly or compute or get some value that they want to be done. Are there any questions about the picture? It hopefully summarizes the different attack points. And now, as we we're also transitioning from noisy qubits to fault tolerant qubits. So just as a reminder, currently we're mostly in the NISQ era where you have the noisy qubits. The machines have a few hundred or a few thousand qubits, but they have all these problems that we talked about. So to one way to address these problems is to just introduce fault tolerant quantum computing with error correction. So you can improve the individual gates, you can improve the individual operations, but on top of that, you can apply error correction, which is what FTQC does. And just a very brief introduction for now. Basically, in fault tolerant quantum computing, you have many qubits that are used to create one logical qubit, and you might see these pictures quite often of a surface code. So each dot in the picture is a qubit, is a physical qubit, and then we call it, so a set of qubits is called a patch. So a patch of an error correction code is just a set of qubits, and for a surface code, you have these square patches where 3 by 3, 5 by 5, or 7 by 7. They're different sizes, and then basically that means how many physical qubits are used to represent one logical qubit. And then the bigger the patch, the bigger the code distance, which means you can correct more errors. But also, if the patch is too big, then these individual qubits and operations might be noisy. So there's like a trade-off. If the patch is too big, then the code might actually not work as well. So it's a whole research area on how you design the error correction. But within the patch, you have data qubits, which are usually shown as at the vertices of each of the squares, and you have some ancilla or stabilizer qubits. So these ancilla qubits are actually used to measure if there are any changes in the data qubits and help with the error correction. And at the very high level, for error correction, basically sort of there are like 5 steps. So first, one logical qubit is encoded into many physical qubits. So one patch represents one logical qubit. Again, since you cannot copy the quantum states, you cannot actually just take one qubit and copy it into 3 physical qubits. what's done is actually you entangle the three physical qubits such that the information is spread across those three or more, or however many qubits you're using. And then you know, once you have a logical qubit, if you're doing some computation, then you apply a quantum gate to transform the logical qubit. So you apply operations to each physical qubit, such the result is that some transformation on the logical qubit. Um, uh, if you're doing computation, if not, then you skip that step. But then at each time afterwards, actually the ancilla qubits, these extra qubits are measured to obtain what's called a syndrome to kind of figure out is there any errors that have occurred. So the way the error correction works is that again you cannot directly measure the data qubits because you would destroy them and lose all the information. But what you measure, you end up measuring basically the correlation between the data qubits, and then if some of them have flipped, then that will show up in the syndrome. And then the critical part then is that now there's a classical computer that analyzes the syndrome to figure out which data qubits might have flipped, and then it tells the quantum computer to apply some gate to a physical qubit to flip it back. So in the error correction, you don't actually measure the data. You basically measure correlation. You guess which one of these physical qubits might have had a problem, and then you kind of flip it back to make sure that the information is not in error. And then this cycle, you detect, you measure the syndrome, you decode to figure out where's the problem, and then you apply some correction. So this is kind of maybe a nicer picture of showing like, and this repeats forever. So as long as the fault-tolerant quantum computer runs, this repeats forever, which means that these are sort of the three steps where you might have some security issues. So one interesting problem is that now you have a classical computer in the loop that's doing the error correction. So then one of the issues that you could have fault injection. So if you can manipulate the decoder that's decoding the information, then that can be a way of injecting some faults or manipulating how the circuit operates. Now, of course, when you measure the ancilla qubits, there could be some problems with the readout logic, for example, or the syndrome measurement. So any faults in the readout logic or the syndrome measurement would, if you can fault that would propagate to the decoder, which would give you the wrong, would decode the wrong steps. And then if there's an error, you apply some quantum gate to fix one of the physical qubits. And again, if there's a problem in that fix, then you incorrectly flip the qubit. So these are sort of the three parts of the fault tolerant quantum computer cycle where you might have introduced some problems sort of on top of what we talk about for the physical qubit. So this will be sort of one layer up. And then so what are some similar for NISQ? So what are some sources of noise or problems? So again, the physical qubits and the gate problems remain the same. So at the bottom, you still have the same physical qubits and gates that could be noisy, imperfect. But now you also have the decoding algorithm running on the decoder to do the error correction. So for example, the decoding algorithm might not account for certain errors like correlated errors, which is hopefully what a lot of the projects will focus on this year. And then again, since you have a classical hardware on top of which the decoder is running, if you can have some faults or side channels in the classical hardware, that will propagate to the circuits. So how can this be abused again by the attacker? So regarding physical qubits and gates, it's the same kind of fault injection or side channels based on the operation of the gates. In the decoding algorithm, you could inject some faults into the qubits. or have side channels. And then for the classical hardware, again, you have fault injections or side channels. So these are all things where you could have the problems. There are much less research for fault-tolerant quantum computers than NISQ machines. So hopefully the projects will focus on this part. This is the next the next sort of next frontier. But yeah, so these are so on top of the physical qubit problems, the decoder and the classical hardware are sort of the new things in the fault-tolerant quantum computers. Okay, so to kind of move on to the next part and kind of put things in context. So basically, now we have four sort of you could divide things into four thread categories that we'll talk about. So we'll talk about these four thread categories. Actually, the first one today, and then the rest on Thursday. And then once we talk about the thread categories, we'll put them together into different thread models. But the thread categories, I guess, unsurprisingly, you have fault injection or side channels. These are the two main problems, and then applied to either NISQ machines or fault-tolerant quantum computers. So, for example, for the fault-tolerant attacks on NISQ machines, again, you can mess up the gates. Similar for fault injection on the FTQC. Now, one interesting thing is that for NISQ machines, since users have access directly to execute the gates, it might be actually easier to do fault injection. In fault-tolerant quantum computers, at least the way they're envisioned, is that each user will have access to a logical qubit, which might actually make it more difficult to abuse the machine. So you can think of it that maybe, NISQ is sort of like, being able to control the voltage of your CPU and each instruction. And then FTQC is more like you just have the assembly instructions, right? So if you have only access to the assembly instructions, it's much harder to mess up the computer. If somebody lets you to control directly the voltage of the computer, it's much easier. So as we move to NISQ, some things will become harder to do, like fault injection on the qubits will probably be much harder. But then there are new problems like the decoder. What if you mess up the decoder? So it's kind of different type of threats, and so that's why I want to cover these categories. Okay, so in the next few minutes, I wanted to kind of talk about the fault injection on NISQ and talk about the different fault injection threats in NISQ machines and have like a little categorization that we can follow. Kind of maybe small detours again. So why would you want to do a fault injection attack? So for all the fault injection attacks, whether it's NISQ or FTQC, basically the main reasons, you modify let's say modify the inputs to the computation so you get wrong results, directly modify the results, or even try to force the computation into a specific outcome or result. So most of the fault injection attacks end up being more like a denial of service attack where you change something and you get a wrong result and you mess up the computation, but let's say it's just sort of a random wrong result. I think the ultimate goal of fault injection, which hasn't really been demonstrated very clearly, but it would be that can you cause a fault that drives the system into a specific state? That would be much more powerful. That you can, instead of outputting state 0, 0, you output state 1, 1, and that deterministically that would make a fault injection attack better. So this trying to force the output of a computation to a specific state, I think is like the ultimate goal, although it hasn't been really done reliably. And then again, in classical computers, there's a lot of examples of fault injection on DRAM, on CPU, on memory buses, kind of all the components that you can think of. Although in many cases that requires physical access to actually glitch the voltage or the clock. So in quantum computer, for the fault injection, assuming like the classical part is already explored, kind of we want to focus on the controller and the QPU, which are the new parts from the right side of the figure. So so we have kind of categorization of the different faults, and um, in the fault categorization, basically we look at the so one aspect is where the fault shows up. So does the fault show up as a wrong gate? So if you inject a fault, does it look like a certain X gate became a Y gate? Something like at the gate level, or does it show up at the pulse level? Like there's a wrong control pulse that's generated. So this is sort of where does the fault manifestation is where the fault shows up, or how it shows up in the program. And then, but to create that fault, you have to target something. So the fault target is what you are targeting, and then the fault target, kind of unsurprisingly, basically corresponds to the components of the system, right? So if you're you can target like a coprocessor, you can target the controller, or you can target the QPU. So you target something in the system, and it shows up uh, at the program level or the pulse level as a result. So for example, um, maybe through some voltage fault on the controller, the control pulses that are generated have the wrong amplitude, and then that shows up as a wrong pulse that's executed on the qubit. So you do something at the QPU or sorry, the controller level, and it shows up in the pulses. Or in the QPU, maybe you do computation on set of qubits that through crosstalk that affects another set of qubits. So again, maybe it shows up as some qubits got flipped, so it looks like there was an X gate that was executed. So the fault targets are specific to the hardware, and then within each piece of hardware, you can target specific things. Like for QPU, you can either target the qubits or the couplings between the qubits, or for the controller, you could target maybe the control pulses or the classical memory that's used in the controller. So so these are the targets. So now we can kind of start with the fault injection classification, where basically we try to show all the parameters that we can think of. So the fault target is where the fault is being injected. Then there's a fault model, which is basically the type or how the fault behaves. The fault bound basically means like how many faults there are, and then fault lifespan is how long it lasts. So maybe you've heard of from other courses, like in a classical computer, you have like sort of some transient fault. Maybe there's like a cosmic particle that strikes your computer, and then one bit gets flipped somewhere in memory. But maybe you have some persistent faults that some logic gate gets stuck at a certain value. So the fault can, you can cause a fault that sort of happens quickly and goes away, or you can cause a fault that crashes the system and lasts forever. And so these are different type of faults to consider. So when we start with the classification, we have again the different targets from the bottom of the pyramid. Again, either the QPU, the controller, or the coprocessor. So more specifically, you have either the qubits or the couplings. If this is mainly for superconducting qubits, for like neutral atoms where you can move around the different qubits, it might be interesting if there are additional fault targets. In neutral atom, there isn't really a coupling because you're just moving the atoms around, but then you have the lasers that are used to interact the qubits. So these targets are specific for superconducting machine. They might change for a different machine. The controller has sort of two parts, and you have either you could target the control pulses more on the RF side once they're generated, or more on the digital side. So the control pulses are generated through digital to analog converters. So if you can mess up the data that's going into the digital to analog converter, of course, the output is wrong. So you could target the sort of the digital specification, some memory that's holding the pulse shape information, or you could target other things like, for example, classical registers or maybe DRAM, any component in the uh, in the uh, in the controller. And then again, in the classical coprocessor or sort of if a GPU is used to kind of operate on some of the data, classical data, you can target registers and other things. So these are sort of the default target. So each fault, when you define, for example, a thread model later on, you have to decide what is the target of the fault. Is it the QPU, or is it the quantum computer controller, or maybe everything if you want to cover everything. And yeah, and there are many different components within each target. And if it's a different type of a quantum computer, maybe the QPU targets are different. The controllers are probably going to be the same for all the types of, well, not all is a dangerous word. The controllers in general probably same problems that you have the analog part and you have the digital part that will probably exist for most of the machines. And the classical coprocessor will also exist for all the machines. So now that we have the different faults for each target, there's a fault model, basically, and they're very specific to each target or each machine. So for the QPU, there are three possible fault models. So one fault model is that basically the fault behaves like a unitary operation. So unitary operations, so all the quantum gates are unitary operations. So a fault might behave that you wanted to apply one type of gate, but you ended up applying a different type of gate. So that would be like a unitary type of operation that it still performs a transformation, but it causes the wrong transformation to be performed. The fault could also be like a non-unitary operation, which basically means like that you collapse or you lose the quantum state. It's not reversible. So maybe a fault causes unexpected measurement, and then that collapses your state. So the fault could look like a non-unitary operation, and then maybe like enable or disable. Basically, for example, turn off disable a qubit so it doesn't work correctly. So or disable the coupling so you cannot do 2-qubit gate operations. So these are the different types of the fault model is specific to the target. So again, so for qubits, these could be like unitary operations or non-unitary operations. For the control pulses, for example, for the analog signals, you can think of the different properties like amplitude, phase, the envelope, or the shape of the pulse. So if your fault could change the amplitude, which might, for example, disable the gate or shift the phase or change the shape. So all these are kind of things that the fault could behave like. And then for the classical registers, for the digital part, it's very same as as before. Maybe from some digital design courses you heard about like stack-at fault. So you could cause some register to always be 0 or always be 1, or you toggle or you flip bits, or some bits get flipped. So those are the type of faults. And again, the things doing the digital part are the same as before, but the new fault models and fault targets are really on top for the QPU and the analog part of the controller. And then this is maybe not so interesting. Fault bounds, you can have either single fault or multiple fault. So if you have single fault, it's easier to introduce single fault. If you have multiple fault, then you have to, the attack has to be maybe more persistent. So, but maybe multiple faults give you different result. And then as last one, this is actually kind of interesting and also maybe a little bit specific to quantum computing systems, that how long does the fault last? So I briefly alluded earlier that each quantum circuit is executed many times to collect the output probability statistics, and then each execution is called a shot. So, for example, a fault could last just a single shot. So, one execution of the circuit is faulted, but others are not. It could last for multiple shots, and as you go down, it basically lasts longer. So, for a single job, basically means for one, when you execute full circuit, like say 1,000 shots, each shot for that job gets faulted. Uh, and then so, a single shot might be easier because the attacker has to modify just one execution of the circuit. For a single job, that means that, say, the attacker has to kind of be always running or always be injecting something as for the whole execution of the circuit. We haven't talked about calibration cycles, but for noisy quantum computers, the noise profile changes constantly, actually. And then, so usually every few hours, the machine is recalibrated. So, at least once a day, but maybe quite more frequently, you do some measurements to figure out the noise profile. So maybe a fault, maybe you can, somehow mess up the qubits that they're not working correctly. But then when the machine gets recalibrated, everything goes away. So the fault could last for a calibration cycle, and then um, power cycle basically means some problems with qubits might not be able to be fixed unless you literally warm up the whole fridge and then you cool it, like you really power cycle the machine. So that's one, and forever basically means you destroy something. Like if you can cause something to never work, then it's like a forever. So these different so I think to kind of wrap up for the fault injection classification, these are sort of the different targets, the models, and then the lifespan. And then for quantum computing or things that are maybe you could draw something similar for classical computers. The more unique parts for quantum computing are the fault targets with the qubits and the analog signals, and then also this idea that now you could target single shot of a execution or a single single job. So the granularity of the fault, like in classical computer, it's maybe you target one instruction, but the program always executes once. Here you have multiple shots. When we talk about the fault injection for fault-tolerant quantum computers, quite similar, but for example, for the fault lifespan, maybe you target each error correction cycle. So there's like another step in there that maybe your fault goes into one error correction cycle or many error correction cycles, which would also be really cool for some of the projects to explore. So these things will change a little bit for fault-tolerant quantum computers. Okay, so maybe we're a little early, but this is basically what I wanted to cover about the fault injection on NISQ machines, and then next time, yeah. So we covered the different threats in quantum computers for both NISQ and FTQC, and very preliminarily talked about the structure of a circuit and which parts of the circuit you might attack, and talked about the fault injection in NISQ specifically. So next time we'll talk about the side channels in NISQ and then fault injection and side channels in FTQC to kind of cover all the categories and talk about the threat models as well, and also the projects finally. So yeah, so that's it for today. Let me stop. Okay, stop.